Um, well, uh, well, thank you very much, Rachel. I apologize for the short delay in getting this talk started. There are a couple of slides that would have had videos, but unfortunately they won't have videos today, but I'll try to sort of act out what the videos would look like to the best of my ability. This is an image called the Hubble Deep Field. This is probably one of the most famous images in astrophysics. It's an image that probably many of you have seen before. This is an image that was made by taking the Hubble Space Telescope and pointing it at a little tiny patch of the sky that looked otherwise completely dark, just about 2.5 arc minutes across. And that's about the same size as the head of a pin would be, held at arm's length. So the Hubble telescope stared at this little tiny patch of the sky for hundreds and hundreds of hours. And this is the image that eventually came into focus through the telescope. And each one of the little points of light that you see here on this image are not stars, but they're actually galaxies. Each one of these with hundreds of billions of stars. So if you count up all the galaxies in this image, there's something like 10,000 or 15,000 galaxies here. And if you extrapolate across the whole sky, that means that just in the part of the universe that we can see, there's hundreds of billions of galaxies, again, each one of them with hundreds of billions of stars. So the point here is that the universe is an incredibly big place. There's an awful lot of stuff out there, just in the part of the universe that we can see. And I think when we think about that vastness of space, how big the universe is, I think the first question that comes to many of our minds is well, could there be other planets out there? Could those hundreds of billions of stars and hundreds of billions of galaxies, could they themselves have planetary systems going around their stars like we do here in our own solar system? And the answer to that is unequivocally yes, and we're going to talk a little bit more about what we've learned about extrasolar planets. But I think once we start to think about planets and planets around all these other stars that exist, we start to think about life. Could there be on these planets around other stars in our own galaxy and other galaxies? Could there be life like arose on our own planet? And I think if we continue down that train of thought, we start to think about intelligent life. Is it possible that somewhere amongst these hundreds of billions of planets around hundreds of billions of stars in this vastness of space, could intelligent life have arisen? Perhaps something like the life that we have on our own planet. And perhaps could that life have evolved a technological capacity far exceeding our own? The universe is very old. It's almost 14 billion years old. So there's a lot of time for very advanced civilizations to have grown far beyond our own technical prowess here on Earth. So this is an incredibly profound question, and I think it's been recognized by many people, not just in the scientific community, but also just in the public. It's really incredibly profound to imagine that around some of these other planets that are being discovered, that there could be other life and perhaps intelligent life. And that's exactly what we try to answer in SETI. That's the question that we're trying to determine, is whether or not we're alone as intelligent beings in the universe. So we call this field the search for extraterrestrial intelligence, but really it's a search for extraterrestrial technology. We don't have any way of directly detecting intelligence. It would be very difficult for us to determine if there were some kind of intelligent fish-like creature swimming around in the oceans of Europa or something of that nature. So we have to use some kind of a proxy for intelligence, and we use technology. Certainly the technology that we have on our own planet is capable of producing electromagnetic emission that's powerful enough that we could detect it at very, very large distances, interstellar distances. And those can be the sorts of things that maybe you imagine when you think about SETI, like radio signals, but also very powerful laser signals that we produce for things like adaptive optics and astronomy. These types of signals would be detectable at very, very long distances with the right kind of equipment. So we concentrate our SETI searches in what's called the electromagnetic spectrum. And this is a plot of the electromagnetic spectrum. Here you see some kind of electromagnetic radiation that you're probably familiar with, optical light. But of course, there's all kinds of different electromagnetic radiation, everything from radio waves down here at very long wavelengths to high-energy X-rays and gamma rays here at the shortest wavelengths or the highest energies. And this shows a plot of all of the different types of electromagnetic radiation that reaches the Earth. So the ionosphere and the atmosphere of the Earth blocks certain wavelengths of light from getting down to the Earth. But there are windows that do get to us all the way from space. So, of course, in the radio portion, we can receive electromagnetic radiation from space. And also, when we look at stars, we're looking at optical light that comes through the atmosphere that reaches all the way to the surface of the Earth. And we try to conduct searches for extraterrestrial intelligence, so searches for evidence of technology everywhere that we possibly can where this electromagnetic radiation falls on the surface of the Earth. And in the radio portion of the spectrum, we call that radio SETI. That's maybe the SETI that you're familiar with if you've read a little bit about this. But we also have optical and infrared SETI that I'll talk a little bit more about, where we search in the optical or the infrared portion of the spectrum. And again, this is basically, we don't have any idea where we're going to sense a signal from an advanced civilization. So we want to search as much of the electromagnetic spectrum as we possibly can. So we have a couple of examples of radio sources that we have here on Earth that are very detectable at very, very large distances. So two of those are the Arecibo planetary radar down here in the bottom right, and something called the space fence radar up here in the top left. So the Arecibo telescope, maybe you've heard of this before, usually this telescope is used to receive radio signals. It's used as a radio telescope. But it actually has an active transmitter on it that's used for radar imaging of asteroids and other bodies in our own solar system. And when that radar is active, this is the most luminous radio transmitter that we have on the planet Earth. And this transmitter could be detectable across the galaxy with the experiments that we do now. And also this space fence radar, this is not quite as bright, not quite as luminous, not quite as visible as the Arecibo radar. But it produces a very, very large beam on the sky. So this thing, again, is very bright, but it only illuminates a really small portion of the sky. So the odds that we would be within the beam of an extraterrestrial Arecibo is fairly small. But some of the very bright radio signals that we produce have very large beams on the sky and would be much more readily detectable. As I mentioned already, we also have optical sources, laser sources on the surface of the Earth. That would be detectable at interstellar distances. And one kind of fun example of that is if you take the most powerful laser that we have, this is a pulse laser that's just down the road at Livermore National Lab that's used for fusion experiments. Take this very powerful laser and we've paired it with some of our largest optical telescopes, like the 10-meter Keck telescopes in Hawaii. This system combined could outshine the sun at 1,000 light years for the brief fraction of a second that laser pulses. Which is really quite amazing. The sun is, of course, incredibly bright. It's very, very luminous and very difficult to outshine. But even with our own technology, if we sort of paired these in the right apparatus, we could outshine our own sun by many orders of magnitude. So the very first radio SETI experiment was conducted by a gentleman named Frank Drake. Maybe this is a name that you've heard of. With a fairly small telescope, about an 85-foot telescope in a little town in West Virginia called Greenbank. And this was called Project Ozma. And this was really the beginning of radio SETI. This is the first what we call modern radio SETI experiment, where SETI was conducted in a way that's very similar to the way that we conduct SETI now. Now, Frank had very limited technology available to him. He had a radio that really wasn't all that different from your car stereo that he could tune around. And he observed just a couple of stars at just a couple of frequencies, near about 1420 megahertz. And of course, he didn't detect anything. But this laid the groundwork for all of the SETI that I think came in the future. And just a couple of years after Frank conducted that experiment, there was a conference that was held where Frank presented the equation that now is sort of synonymous with his name, the so-called Drake equation. And maybe many of you have seen this equation before. Here, n is the number of civilizations that we might be able to detect, the number of communicative civilizations. And then here on the right-hand side of the equation are all of the factors that go into the emergence of technological life or communicative life. R, the rate of star formation in the galaxy, Fp, the fraction of those stars that have planets. And it goes all the way on through here to the fraction of planets that might develop life, a fraction of that life that might develop intelligence, and so on. And this was, I think it's important to point out, this was never sort of meant to be an equation like F equals ma or E equals mc squared. This isn't a sort of an analytical solution that allows us to directly predict how much life we might be able to come into contact with, but more it's a thought experiment. It's just a way of thinking about the different factors that might go into the emergence of intelligent life. So a couple of these we have actually a pretty good idea of now. So just from our studies in astrophysics, we know approximately what the rate of star formation is and the number of stars that have planets. And if you calculate all of these together, you end up with billions of opportunities for life. Something like 1 in 5 of the stars that you see in the night sky when you look out in our own galaxy probably have planets that are something like the Earth, between 1 and 2 Earth radii, and within the so-called habitable zone of their star. They're close enough to their star where liquid water could exist on the surface, but not too close for that water to evaporate away, or too far away for that water to freeze. So these other terms in this equation are much more difficult at the current time to determine. We really don't have any way of testing these yet. But I think we have reasons to be optimistic about them. And in the end, I think this is really a very important point for SETI, and I think Carl Sagan summed it up very well in a sort of an editorial piece that he had in Science Magazine about 30 years ago. And that is that the only significant test of the existence of extraterrestrial intelligence is an experimental one. The only way that we're ever going to be able to test some of the parameters in this Drake equation, the fraction of life that go on to develop intelligence, is to actually conduct experiments to try to detect that intelligence. And that's exactly what SETI is. It's an experimental science that's trying to determine whether or not other life exists and whether that life evolves intelligence. So again, we have a lot of reasons to be very optimistic about this search that we're doing, and I already mentioned this, but really, we hear a lot about planet discoveries in the media. It seems like every week we're hearing about new planets that are discovered by the Kepler mission or by other missions. But the bottom line, the punchline of all of this is that most stars have planets. In fact, probably all stars to zeroth order have planets. And something like 1 in 5, 20%, of all of the stars that are in our galaxy have a planet that's something like the Earth. So it's really an incredible opportunity for life to develop. And of course, that implies that there's something like tens to 100 billion Earth-like planets just in our own galaxy. Of course, many of these planets have been discovered by the Kepler mission. Most of you are probably familiar with how this works. The Kepler mission stares at about 100,000 stars, or at least in the first iteration of the Kepler mission, it stared at about 100,000 stars, and watched for the little dip in light as a planet passed in front of the star. And it was an incredibly successful experiment, and really is responsible for us knowing this fact that something like 20% of stars have a planet like the Earth. And the Kepler mission has found all kinds of different planets, really a zoo of planets, and this is a kind of a fun way of characterizing those in something called the periodic table of exoplanets. Some of them are cold and some of them are warm, some very hot, some very large, some very small. Really an incredible zoo of different types of planetary systems. But importantly, something like 1 in 5 stars has a planet like the Earth. Again, between 1 and 2 radii of the Earth, and in that habitable zone of their star, where liquid water could exist on the surface. We have other reasons to be optimistic about SETI, and just a couple of those I can go through. One of them is that in order for life to evolve, you might imagine that we need some complex chemistry. We need some building blocks for basic life. And we find lots and lots of building blocks literally everywhere we look in astronomy. We found what we call prebiotic molecules, multi-carbon organic compounds in protoplanetary disks all over the galaxy. These are the birthplace of planetary systems, and they seem to be chock full of all of the stuff that we think is necessary for life to emerge. When When we look inside meteorites on our own planet that we find that fall to us from within our own solar system, we can look inside of those meteorites and we find, again, all kinds of complex organic compounds. All of the stuff that we think was necessary for life to emerge on Earth seems to exist ubiquitously in our own galaxy. It seems to be all over the place. And we can do sort of basic experiments to see if maybe we can make even more complicated molecules by replicating the conditions that existed on early Earth. And really a famous set of experiments along these lines are something called Miller-Urey experiments. And the way that these work is that you construct a sort of a glass apparatus that looks something like this. You put some seawater in here, some just sort of basic kind of soup of stuff that we think existed on the primordial Earth, early in the Earth's formation. And then you heat it up, kind of mimicking a volcanic vent that might heat up that seawater. And then you pass it through this is a spark discharge gap, so it electrifies, it sparks the mist sort of comes out of this evaporating stuff here. You shock it, and then you allow it to condense, and you see what comes out. And what we've seen is that even more complicated organic compounds can be synthesized in this way with a purely biochemical origin. So you can take the sort of basic prebiotic molecules that we know that exist all over the place, and with some natural processes you can make even more complicated compounds and move towards complicated, perhaps single cell life. And we've also learned that life can exist in extraordinarily extreme environments on the Earth. So it used to be that we imagined that most life required kind of basically the same sorts of stuff that the ecosystem on the surface of the Earth requires. It needs sunlight, it needs photosynthesis, these kinds of things. There's actually whole ecosystems that exist at the very bottom of the ocean, several miles beneath the surface of the ocean, around hydrothermal vents, where entire ecosystems of organisms survive off chemosynthetic bacteria that live off of chemical reactions involving the hydrothermal vents at the bottom of the ocean. This is an example of these chemosynthetic bacteria. So it seems that there's lots of stuff that's necessary for life. All of the basic building blocks for life are out there. And life can exist in very, very extreme environments. So it doesn't look like life is especially finely tuned to need a very particular set of conditions that might exist on the surface of the Earth. It seems to be able to exist just about everywhere that it possibly could. But I think the real question that sort of comes out of this is, you might sort of accept that these prebiotic molecules exist and that we can take sort of basic prebiotic molecules and we can make more complicated things. But the real question, I think one of the most difficult questions in SETI is, well, is it common for intelligence to evolve? In some respects, we only have one example of an intelligent species that arose on the surface of the Earth. It sort of has the technological capacity of human beings. So is that a fluke? Is that just some sort of random evolutionary happenstance that we happen to evolve the capacity to create technology? Or is evolution somehow sort of driven towards this, and do many species develop a technological capacity? And again, that's exactly the question that we're trying to answer in SETI. So we talked already about the electromagnetic spectrum. This is another sort of example of that plot that I already showed you. So in order to search across the electromagnetic spectrum, in order to search for optical signals and infrared signals and all different variety of radio signals, we need to use many different telescopes. I'm going to show you a few of the experiments that we're doing to try to detect these signals, all the way from the very, very lowest radio frequencies, the longest wavelengths of electromagnetic radiation, all the way up through to optical light. So where would you point a telescope in a SETI experiment? I think this is a really sort of interesting question, and it's a question that even scientists have disagreement about. Many people have different ideas about where we should point the telescope. Of course, stars like the Sun or exoplanet systems that look like our own solar system are very prime targets. Maybe very nearby stars. So of course our experiments are limited in their sensitivity. A transmitter that we detect has to have a certain luminosity or has to have a certain brightness for us to be able to detect it. So maybe we should look at nearby stars, and also, of course, just known exoplanets. We're discovering all of these extrasolar planets. Perhaps we should spend a lot of time on those. And we target all of these different things in our SETI experiments and try not to make too many assumptions about what the best possible target would be in a SETI experiment. So I think one of the coolest things that's come out of the Kepler mission is not the discovery of individual extrasolar planets, but actually the discovery of multiple extrasolar planet systems. So this is one of those animations that I told you that unfortunately you don't get to see. But if this were a video, you would see all of these multiple planet systems spinning around. And this is a plot of all of the multiple planet systems that the Kepler mission has discovered. And so this discovery, our knowledge of these multiple planet systems, and our very accurate information about exactly when these planets orbit their star. So remember, Kepler found these planets by watching the star and watching for that dip in light when the planet passes in front of the star. So not only do we know that all of these systems exist, and we know a little bit about the planets, but we actually know exactly when they pass in front of their star as seen from Earth. And this allows us to do something really cool in SETI, something that we call exoplanet eavesdropping. So many of you probably know that traveling near the speed of light takes a lot of energy. It's very, very difficult. And many people believe that it's so difficult that it's probably exceedingly rare for even a technologically capable species to travel between stars. So if a very advanced civilization started to run out of room or resources on the planet where they first arose, maybe the first thing that they would do is they would colonize another planet in their own solar system. So if they did that, perhaps there would be some communication between those two planets. So using this very accurate knowledge of the orbits of these multiple planet systems discovered by Kepler, we can actually time our observations of these systems using our SETI experiments on Earth to the moment when two of these planets are aligned relative to the Earth. So if the civilizations on these two planets are communicating with one another, we have a chance to eavesdrop on that communication. And this is a very exciting new technique that we're just starting to use in some of our experiments. So this is a telescope that we just started using. I'm sort of going to start with kind of the most recent experiments that we've been conducting in SETI. And I think, so Rachel mentioned that I have a joint affiliation with an institute in the Netherlands, a couple of institutes in the Netherlands. And the reason why that exists is that we're trying to take advantage of this new European telescope called the Low Frequency Array. And the really special thing about this telescope is that it's sensitive to very, very long wavelengths, very, very low frequencies of radiation, much lower than we've ever been able to search for in the past. And actually, it's sensitive to the same radio frequencies that we use for our radio and television here on the surface of the Earth. So you might think that maybe this would be a very obvious place to conduct a SETI experiment, but historically, not very many SETI experiments have been done at these frequencies. And so we're very excited to be conducting a search of the nearest stars to the Earth, the 30 or so stars that are within about 15 light years of the Earth in the northern hemisphere. And we just completed these observations at the end of 2014. And the analysis of these data are underway. And we're very excited about this experiment and also other experiments that we're going to be able to do to look at these very long wavelengths, these low frequencies of radiation. There's a brand new telescope in that little town in West Virginia where I told you that Frank Drake conducted the very first SETI experiments called the Green Bank Telescope. This is the largest fully steerable radio telescope in the world. And by fully steerable, I mean that this whole structure can move and can point sort of just about anywhere that's above the horizon from this facility. And it has a very, very broad frequency coverage, so it can look at a lot of different radio frequencies. And beginning about 5 years ago, we've been using this experiment for SETI. And the very first experiment we did with it was to look at some of those Kepler planets that had been discovered by the Kepler mission. And we published a paper about a year and a half ago on some of our first results with this telescope. And we came up with sort of two kind of important punchlines, I think, from that work. And something like less than 1 in 10,000 stars hosts a civilization that has a radioluminosity that's somewhat comparable to what we can produce on Earth. So less than 1 in 10,000 stars has a radio transmitter as bright as our brightest radio transmitter on Earth, that Arecibo radio telescope that I talked about earlier. And something like less than 1 in a million stars hosts a civilization that has a very, very bright radio transmitter. So if we imagine that some very advanced civilization could produce a very, very bright radio signal, less than 1 in a million stars hosts a civilization like that. Sure.
Where did those results come from?
Yeah, so that comes from taking the sensitivity of our experiment and assessing the number of stars that we were able to observe, and then you can come up with a limit, sort of a lower limit. Another telescope that we use quite a lot is this Arecibo telescope. And remember, again, I told you that this telescope is usually used just to receive radio signals, and we use it in SETI for that purpose. And we have a whole bunch of different experiments here at this telescope. The really cool thing about how we use the Arecibo telescope is in something called a piggyback or a commensal observing mode. So what that means is that we've come up with a way of using the Arecibo radio telescope to do SETI when any other kind of radio astronomy is going on with the telescope. So rather than having to take control of the telescope and point it at certain places and use up observing time, we actually have a way of just listening in on the data that comes from the telescope while other people are using it, and then doing a parallel analysis for SETI. And so that's a fantastic kind of experiment to do, because the Arecibo telescope is huge. It's 300 meters across. It's very, very sensitive. But if you're using the telescope basically 24 hours a day, 7 days a week, it generates a huge amount of data. And figuring out how to analyze that data was a real challenge. And so what the group came up with was something called SETI at Home. This is a screensaver, a program that you can download on your own computer. And when you start up the program, it takes a little bit of data from our computers in Berkeley and processes it on your computer, and then sends the results back to us. And here you can see sort of the schematic of how that works. You have work units, you have little bits of data being sent out to volunteers that run the program. You have work units being sent back, so results of the processing being sent back to Berkeley. And a number of different data sources. So historically, all of the data for this SETI at Home program is coming from Arecibo. But we're very excited to be adding the capability to this software so that it can process data from other telescopes, including the low frequency array that I talked to you about, and also the Green Bank telescope. So if you run, how many people here run SETI at Home or have heard of SETI at Home? So if you still run SETI at Home, or if you're excited to give it a try, stay tuned, because very soon, in addition to being able to select how much of your computer power goes to this program and when it runs, you're also going to be able to select where the data comes from that you process on your computer. And here's a picture of the screensaver. Again, this would have been animated, and it's much more beautiful than this image would. This image shows. But it's really a fun thing to try on your computer. It shows you exactly where the telescope was pointed when you were processing, what frequency you were looking at, and also kind of what types of signals the SETI at Home screensaver is looking for. So really the advantage of SETI at Home is that it allows us to search for a huge, wide variety of signals. So when we conduct a SETI experiment at an observatory, where we use the computers that we're able to bring to the telescope or the computers that are available at the observatory, we're limited in the number of different types of signals that we can look for. So some of you might say, well, what kind of radio signals do you look for? And usually it's narrowband signals. And often if there's electrical engineers in the room, they say, well, what about wideband signals? What about signals that are more similar to our modern kinds of radio communication? Because SETI at Home has so much computing power available, it can search for those wideband signals and a whole variety of other types of signals as well. So SETI at Home was incredibly powerful, I think for SETI. but it was also really kind of laid the groundwork for a whole generation of what we call distributed computing projects. So the type of technology that we use in SETI at home to process radio telescope data to look for signals for extraterrestrial intelligence are now used by a whole slew of other researchers that have very computationally intensive problems that they can't get supercomputer time to solve. And just a couple of those are protein folding programs and also climate prediction, and there's hundreds of different types of science that you can do with this same infrastructure that was built up for looking for extraterrestrial intelligence. And a second extension of that that many of you are probably familiar with is the idea of, well, why not, instead of just using your computing power that you have at home, why not also use your eyes and your ears and your brains to contribute to scientific challenges? And so that gave rise to something we call BASA. This is an open infrastructure for distributed thinking. So a way of actually allowing you to not just run your computer to process some data, but actually look at the data that you're analyzing and make judgments and use your sort of human capacity that computers can't yet capture. And the first experiment that we did along these lines was with a spacecraft called Stardust. This was an experiment that sent a satellite out beyond the orbit of Mars to capture dust grains, interstellar dust grains that are floating around in our solar system, to try to learn about what the solar system was like when it first formed. And the way that this experiment worked is that there was a big panel that unfolded from the spacecraft with a special substance in the panel called aerogel that could capture these dust grains when they slammed into the spacecraft. So it was just like a sort of a strainer that the spacecraft held out and swept along as it floated out past the orbit of Mars to capture these dust grains. And then this panel was returned to Earth. And the challenge of this experiment was to search through all of these little chunks of aerogel, all of these substances, to try to find these individual particles that were collected by the spacecraft. And in order to do that, it was calculated thousands of years of analysis for an individual researcher to take very, very careful images of all these little chunks of this aerogel to look for these particle tracks. And this is something that computers aren't very good at, but the human eye and the human mind is very, very good at. And so using this infrastructure that we talked about, we put together a special kind of website that you could go to where you could kind of have a virtual microscope that allowed anyone in the public to actually look at the same images that a scientist would look at and could be trained to actually find these little dust grains. And there was something like 50 to 100,000 people that participated in this experiment. About 50 of these particle tracks were discovered, and the very first interstellar dust grains that were discovered by this mission were actually found by a public volunteer. And so I think this is an amazing example of really what the internet and an interested public can accomplish in science. And we're very excited about this idea for SETI as well, and we've been thinking about ways to not only take advantage of people's computing power again, but also their minds to try to perhaps be sensitive to signals that we haven't thought of before. And there's a number of other projects that have come out of this, including mapping craters on the moon and looking for fossils in the African desert and a variety of other things. And if you're interested in these kinds of projects, I really encourage you to check out our website. The URL I'll give you in a second. And another project that is very similar is the Galaxy Zoo. So this is a project to categorize the morphology of galaxy shapes. This is not a project that's done by our group, but sort of very similar in spirit to what I've talked with you about already. And I think many of you probably you're coming to this lecture, you probably know about a lot of these projects. I think we're really in a golden age of citizen science. It's really an incredible time, not only to be a scientist, but just simply to be interested in science, because there are so many opportunities for you to engage in an incredibly meaningful way in the research that I've talked about today, but also a huge variety of research in fields well outside of astronomy. So the experiments that I've talked with you about so far are our radio experiments. But as I said, we also conduct experiments in the optical portion of the spectrum. There's a number of advantages to optical signals, but I think really the one that I find most compelling is that the information capacity of a signal is proportional to bandwidth. So if an advanced intelligence, suppose they wanted to intentionally signal us, a radio signal might make a lot of sense. It's very easy to pick up against the sort of background static of the universe. But in many ways, it's really just a kind of a binary signal. It's sort of on or off. It's one bit. There's not a lot of information there. But if a very advanced civilization wanted to transmit a huge amount of data to us, if they wanted to send us the so-called Encyclopedia Galactica, some trove of all of the knowledge that they contain, they might pick something like an optical signal to do that. And we have a couple of new experiments, one that's absolutely brand new, that's just going to go on the telescope in about a month, to search for optical signals at Lick Observatory. And that's, of course, just a couple of hours south of here. This is a project that's led by a professor at the University of California, San Diego, named Shelley Wright. And the new experiment that we're doing at Lick is going to allow us to look into what's called the near-infrared portion of the electromagnetic spectrum for the very first time. So the near-infrared are wavelengths that are just a little bit longer than optical light. And so you might, sort of on the surface, not think that really means a whole lot. But it turns out that near-infrared light is very, very exciting for astronomy and very, very exciting for SETI. And the reason is that near-infrared light can get through the dust between the stars much more readily than the optical light. So this is an optical image of the Milky Way. This is the plane of the Milky Way galaxy. And you see all these little kind of dark splotches in here. Those are dust lanes. They're clouds of dust and extended clouds of dust that are blocking optical light from reaching us from those portions of the galaxy. And here's a very similar image, but just a little bit longer wavelengths in the near-infrared, and you see all of those dark splotches are gone. And that's because that near-infrared light can get through the dust between the stars much more readily. So in a SETI experiment, that allows us to see much more deeply into the galaxy. It allows us to probe many, many more stars, and gives us a much better chance of detecting an extraterrestrial laser were it to exist. Yeah? Well, so what you see here are largely individual stars. Some of these are, of course, galaxies. The point spread function of the telescope, I think, is a little bit coarser here in the near-infrared image, so the resolution just isn't quite as good. It also might partly be sort of the fact that I exported this to a PDF, so maybe it just didn't come through quite as well. But these are very similar images in the sort of the projection that they're showing. Another telescope that we're very excited about using is called the FAST telescope. This is a telescope that's being constructed in China. It's sort of a Chinese version of the Arecibo telescope. So I mentioned that the Arecibo telescope is 300 meters across. The FAST telescope will be 500 meters across. So significantly more sensitive, something like a factor of 4 more sensitive than Arecibo. And the Chinese group of astronomers that's in charge of the science for this telescope are very excited about doing SETI with it, and we've been working with them very, very closely. And this not only will allow us to have a whole nother source of data, a whole nother telescope to look at for SETI, but also this telescope, because of the way that it's built and where it is, it will have access to a different and in some cases larger portion of the sky than we have access to with Arecibo. So maybe some of you have heard about this brand new radio telescope that's being built called the Square Kilometer Array. This is an effort to build a radio telescope that has something like 10 times the collecting area of even FAST, even our very largest radio telescopes. This will be something like 10 times more sensitive. And And this telescope is going to be built in South Africa and in Australia. It's actually made up of a number of different separate telescopes, each of which is made up of a whole bunch of dishes. Really the punchline, I think, for the square kilometer array is that this telescope will, for the first time, allow us to be sensitive to radio signals that are about the same sort of energy level as the leakage radiation that leaks off of the Earth. So the sort of radio signals and TV signals that we produce on Earth are really undetectable to our current generation of experiments, even from the very nearest stars. They're just too weak. But another factor of 10 in collecting area, a factor of 10 in sensitivity, will allow us to be sensitive to those signals for the very, very first time from about 5 of the nearest stars, which is really a dramatic step forward for radio SETI and something that we're very, very excited about. There's also a number of missions that are kind of successors to Kepler and successors to Hipparcos and to other sort of astronomy experiments that have been done in the past that are going to dramatically increase the amount of targets that we have to look at in SETI experiments. So the Kepler mission, we talked a little bit about that before, that looked at about 100,000 stars, but those 100,000 stars were themselves about 1,000 parsecs or a few thousand light years away from the Earth. It was one little patch of stars that were quite distant. There's a similar experiment that's going to be launched in a couple of years called TESS, the Transiting Exoplanet Survey Satellite, that's going to use the same technique as Kepler. It's going to look for that dipping of light from the star, but it's going to look at stars that are very, very near to the Earth. So it's going to find similarly many, many exoplanets, probably 100 or a few hundred extrasolar planets from TESS, but it's going to find them very, very close to the Earth, and these are going to be real prime targets for our SETI experiments. There's also a satellite that's already up and is already starting to produce data called Gaia that's going to catalog something like 1 billion objects within our galaxy and in some cases outside of our galaxy. And this is going to basically tell us every single star within a few hundred parsecs, what type of star it is, of course, where it is, the age of the star, all of those kinds of things. So if we want to do a systematic search of the nearest stars to the Earth, the catalog produced by Gaia is going to be really fantastic. So in the last couple of minutes here, I wanted to return to the Drake equation, just to point out something that I think is really incredibly profound about this equation. And that is the last term in the equation, L, the average lifetime of a civilization. So on the surface, this doesn't really seem like something that you can probe in such an experiment. But in fact, by measuring the presence of extraterrestrial intelligence, we actually can infer the lifetime of intelligent civilizations. And this is something that a very famous engineer in SETI named Philip Morrison called the archaeology of the future. So the idea here is that because of the finite speed of light, when we receive a signal from some distant star, we're seeing that civilization as it was maybe 500 years ago or 1,000 years ago or maybe many thousands of years ago. But because the universe is so old and our civilization is so young, it's likely that civilization is far more advanced than we are in terms of their technological progress. So by looking at this other civilization's past, in many ways we're looking at our own future. And we're learning whether or not it's possible for advanced civilizations to survive hundreds of years or thousands of years, maybe hundreds of thousands of years after they've developed technology. Sure? Oh, well, I mean, probably a science fiction movie is a better answer to that than I can give you. I think maybe we can, I just have a couple more slides, so maybe we can finish, then we can talk a little bit more about that at the end. Again, I think, really the promise of SETI is this ability to answer this question, or at least give us some insight into what our civilization might be like 100 years in the future. Is it possible to survive the sort of dramatic increase of technology that we're seeing now, is it really possible for humanity to survive? And, you know, can we make it 10,000 years into the future? Is it possible for a technological species to make it 10,000 years into the future and to construct vast spaceships that might allow us to explore our own solar system and maybe beyond? Again, I think that this is really the most profound aspect of SETI is the opportunity to get some insight into this question. And with that, I'll take the rest of your questions. Thanks. So we'll come back to yours maybe, but right here. Yeah, no, we haven't. There have been a number of times when in a SETI experiment we found a signal that looked pretty good. And sometimes it's taken us a few hours or a few days to follow up on the signal and determine that it was actually some artifact of our own technology that we were seeing. But no, we don't have any outstanding candidates.
What I'm hearing most scientists like myself working in the field believe that there is life somewhere out there, and yet we have these magazines like Time Magazine, National Geographic, asking over and over again, are we alone? How can scientists like yourself help to change the popular paradigm that seems to think that we are alone into one where it's a given that we're not alone? And the problem is just, where are they?
Yeah, well, so it absolutely is not a given that we are not alone. The truth is that we don't know. I mean, despite, you know, hundreds of years, thousands of years of astronomy and you know, 50 or 60 years of really kind of modern astronomy, we only know of one example of life anywhere in the universe, anywhere, even in our own solar system, and that's on the planet Earth. So for the moment, it's an outstanding question, and I think sort of posing the science as a question, are we alone, is probably the most accurate way to pose it. You know, I think you know, and there's sort of in the scientific community, I'd say there's sort of two kind of camps. There's what I like to call the physicist camp, which is that if something happens once, it probably didn't happen only once in the entire universe. It's probably happened a few times. And I my own sort of thoughts on the matter probably fall sort of in line with that idea. I think that it would be awfully strange if we were the only life anywhere in the universe. But there's also the biologist camp. And I think many biologists look at the question of the emergence of life on Earth and say that, well, it's quite possible that it only emerged one time, that it really was some just complete random fluke of biochemistry that led to the first life on this planet. I mean, there's lots and lots of planets, right? Lots and lots of water, lots and lots of prebiotic stuff. That's a very, very large number. But then there's some very small unknown probability of life arising. So take a very large number and multiply it by some unknown, really small number. You might get 1, you might get 10, you know, you might get 100 billion. We just don't know.
Yes. One thing that modifies one of the terms for the equation, but it's relatively simple, is the recent findings about the huge role of Jupiter protecting the Earth from being clobbered all the time. And the question then is, how many solar systems have an arrangement where the planet and hammer zone protected in that way?
Yeah, that's a hard question. So there's a number of sort of boutique ideas about, you know, the special conditions of our solar system that allowed life to emerge on Earth. So some people think it was the plate tectonics, some people think it was the presence of the moon and the tides that it rose on the ocean, and some people think it's it's Jupiter, I mean, I think certainly, as you said, Jupiter played a role and continues to play a role in protecting the Earth from large impacts or more large impacts from asteroids than it experiences. We don't know the answer to that. So again, only one example of life. So it's completely unknown. But certainly, I think if as we start to find more exoplanet systems, were we to find an exoplanet system that had a configuration that was similar to the solar system in more ways, perhaps that had a large planet, outside the orbit of a smaller planet that was in the habitable zone, we would spend more time on those targets in our SETI experiments.
So the last term was the average lifetime of civilization that would be able to detect technology and all that. And if that number is really, really small, we'd be really unlikely to detect anything. If it were really, really big, it'd be more likely to detect something.
Yeah.
Is there a threshold for that number?
Well, no, there's not a number. There's not a numerical threshold. I mean, I think, your question is kind of apt. I mean, certainly there is some threshold whereby if all other things being equal, if life doesn't survive for a certain amount of time, it would be extraordinarily difficult for us to detect it. In broad strokes there is one, but not a numerical one that we've yet been able to determine. Again, just because this is a young field and we haven't done enough searches.
So I like this thing that you mentioned of the two planets, lining up. I heard about that before. I wonder how often that happens and how long they stay lined up for looking for that data. I mean, are they actually going to, you or whoever's looking at this, actually going to be able to time things often enough and sort of scatter shot here and there?
Well, so as you might imagine, it's a function of the orbital period of the planets and how large the planets are. So for the few thousand planet candidates that have been identified by Kepler, at any given time, a handful of them are in conjunction, sort of in the geometry that I showed. And a typical duration for those, for like sort of a 50-day and a 25-day orbit set of planets, something like that, is half an hour or an hour or something like that. So it's not hard to find them in that geometry. So all of the in the case of the Kepler mission, all of those planets were discovered in a fairly small patch of sky. So if we asked for telescope time for this patch of sky and were awarded it for some particular set of hours or something, there's always going to be some of them that are in this geometry that we can search. But the most interesting ones, again, if you have one planet in a 150-day orbit and another in a 300-day orbit, I mean, sort of 150 days or so, they're going to be in conjunction. So the more interesting ones are more rare and do require more precise timing to catch them. In the black.
The fact that the Earth's poles are not perpendicular to the planetary plane, it gives it radiation and causes seasons on this planet. Do biologists think that unique fact about Earth's impact on evolution here? And are you looking for that sort of thing also?
That's another one that I didn't mention, an aspect of our solar system that some biologists, as you said, think was very important. And again, as we learn more about exoplanet systems, the ones that we find that look the most like our own solar system are going to be at the highest of the list of the ones that we look for. We just don't have that much information about exoplanet systems now to target systems like that. But if we did, certainly sort of similarity to our solar system, broadly speaking, is a very high-ranking kind of factor in targeting. Right here.
Did I understand correctly? You were saying that Arecibo is also sending. So what are the planets?
Well, so it's used for two purposes. One, to image the surface of other bodies in our solar system, asteroids and moons of other planets, things like that. and also to determine their ephemeris, so to determine their orbit. And the actual type of radio signal that it sends in those two cases is different. But the transmitter is like at about 2.5 gigahertz or so. It has sometimes it has a very narrow bandwidth. Oftentimes it's used in a mode that's precisely similar to the type of signals that we look for in a SETI experiment. Other times it's used in a broadband mode that would be a little bit more difficult for us to detect with our current experiments.
It's not like a mathematical signal or anything like that.
Oh yeah, it uses a pseudo-random code, which just has to do with the way that it performs the imaging when it does it shifts the phase in a particular way to allow it to construct an image. But no, it doesn't encode any sort of information about humanity yet. Well, on the first point, I think we're an awfully long way from kind of theoretical limits. I mean, just to give you an example, you probably heard about various experiments that have been designed that will have some sort of a coronagraph, some occulting system to block out the sort of light from a star to allow it to see very, very large contrast sort of between the star and the planet. And experiments that are going to be designed to look at the atmospheres of extrasolar planets. There's an idea that's kind of on the books to actually use the sun as a gravitational lens. So if you stick a spacecraft out at 550 AU, way far away from the sun, you can actually use the sun as a lens itself as it curves space. So we have lots of room to grow in terms of learning about extrasolar planets. And to the second part of your question, how people can get involved, with SETI, certainly, I think checking out our website, seti.berkeley.edu, seti@home.berkeley.edu. There's lots of opportunities there that you can find. There's a website called SETIQuest, SETIQUEST.org, that's run by the SETI Institute in Mountain View that allows you to participate in some of their searches. And of course, the Zooniverse, Galaxy Zoo. If you Google any of those things, you'll find a lot of projects run by that group as well.
So I think we're